Before we move on and learn how to take partial derivatives of multivariable functions, let's take a moment to review some derivatives and some basic rules that we can apply and actually do algebraically. So there are really four rules that we want to focus on here, and those are the derivative of a constant, the derivative of a power function, the derivative of an exponential function, and the derivative of a logarithmic function. So first of all, the rule pertaining to a constant. So here we're going to define a and b as constants in everything we're about to show. Okay, so the derivative of a constant is always zero, and this d dx notation means we're looking for what is the rate of change of this quantity here. So why is the derivative of a constant zero? Well, if we ask how fast is a constant changing, for instance down here we're going to look at a distance function, and suppose your distance is always 2. Well, if your distance is always 2, that means you're not moving at all, and that means that you have zero speed, which in and of itself tells us that its derivative would be 0. The power rule, which is the one we're probably most familiar with, is the derivative of x to a constant power involves multiplying x by, basically, as we might imagine, dropping that exponent down as a multiplier and subtracting 1 from the exponent. Now the exponential rule says, let's say we have a constant raised to a variable power. Its derivative will be the coefficient a times the natural log of the base b times b to the ax. Okay, so for example, if I have something like the derivative of 3 to the 4x, its derivative will be, in our case, a is 4, that's the coefficient of our exponent, times the natural log of the base, which is 3, times b to the ax. So the derivative still involves 3 to the 4x. However, our coefficient there will change, and 4 times the natural log of 3 comes out to approximately 4.4 times 3 to the 4x. Now we can't multiply 4.4 and 3 because 3 is being raised to an exponent, and exponents are done before multiplication, so the best we could do is leave it like this. Some will even put parentheses around the 3 to the 4x, but it's not completely necessary. Now, if our base happens to be e, and you might recognize that if we have e to the 4x, the derivative of e to the 4x, now this is not d dx times e to the 4x, it means take the derivative of e to the 4x, then we're saying here that it's simply going to be a times e to the ax. Well, why is that, and what does that have to do with this rule? It has to do with this natural log piece here. So if we write it out according to this rule, a in our case is 4, that's the coefficient to the exponent, times the natural log of the base, in this case that's e, times b to the ax, or e to the 4x in our case. Now the natural log of e is 1, and so this simply becomes 4e to the 4x, which you can see that in the case where our base is e, then we get a times e to the ax. And that's exactly what we got here. Now as for logarithmic rules, or derivatives of logarithmic functions, the derivative of log base with a base of b of ax is going to equal 1 over x times the natural log of the base b. Let's take a look at an example. If we want to take the derivative of log base 5 of 2x, now notice that the 2 is not going to be part of the derivative. It does get canceled out algebraically, and so I'm just providing you here with the final, most reduced form of this derivative. So this is going to be 1 over x times the natural log of b. So b is the base, in this case that's 5, and this will be 1 over x times the natural log of 5. And if you want to approximate the natural log of 5, it comes out to about 1.6. So this is 1 over 1.6x. Now again, in the case of dealing with e, natural log and e are nice because the natural log of e is 1, as we demonstrated above here. So if we took the derivative of log base e of x, which is what natural log is. Natural log is log base e. That's just an abbreviation we use for it just because it occurs naturally. It occurs very often, so we just use ln in place of writing log base e. So if you see natural log, then that's log base e. So let's say the natural log of 2x. Well, that's going to be simply 1 over x. The derivative of that function will be 1 over x. So exclusive of what the coefficient is in front of x, provided it's simply a constant, the derivative will be 1 over x. So let's take a look at each of these distance functions over time so we have a little bit of an application, and we want to determine the speed of the car at t equals 2 hours. So the derivative of 2, which we would often write in one of two ways. You could say d prime of t, and the derivative of a constant is 0. So another way of writing this would be just as an alternate notation that kind of makes us realize that this is the change in distance per change in time. Your change in distance per change in time is 0 over 1, and assuming distance is in miles and time is in hours, you're traveling at a rate of 0 miles per hour. And that makes sense if we look at the graph of this function. The graph of this function will be a horizontal line, and notice that our distance isn't changing. We're basically in the same place. We're 2 miles away from home at all times. Now we didn't write this, but when we take the derivative of a function that has addition and subtraction, we take the derivative of each term separately and then add them together. So the derivative of 2t, which is 2t to the first, will be, first of all, multiply, drop down that exponent and multiply. 1 times 2 is 2. Subtract 1 from the exponent, this will be t to the 0, and t to the 0 is 1. Now the derivative of 5 that's the derivative of a constant, which is 0, and so we get a derivative of 2. Once again, we can write this as dd dt, and so we're seeing that the change in distance per change in time is always 2 over 1 miles per hour. And if we graph this, we could see that it doesn't really matter what time we're looking at 1, 2, 3, 4, 5. Every time you increase t by 1, your distance will increase by 2. So this always has a slope of 2 to 1. And once again, that's why the constant didn't matter. That's just where we started. We were 5 miles away from home at time 0, and then each hour, our distance was increasing by 2. So at t equals 2, for these two functions, the rate of change is constant. Here it's 0, here it's 2. Now here's where things get a little more interesting. Now we know that this function is quadratic, and so it's not linear. If I take its derivative, I get, by the power rule here, 2 times 4 is 8. Subtract 1 from the exponent. The derivative of 3t is just going to be plus 3, as we have an exponent of 1. 3 times 1 is 3. T to the 0 is 1, and so we can just leave it like that. And the derivative of 15 is 0. So now my derivative function depends on the value of t that you give it. So your speed will be different at different times. And if we want to figure out what's our speed at time 2, we could write this like this, or we could even write d prime of 2, but I like to use this notation because it emphasizes that the value will be a change in distance over change in time. So if I plug in 2 for t, 8 times 2 plus 3, I get 16 plus 3 equals 19. Again, I'll place that over 1 because this is the change in distance in miles over 1 hour, and we're traveling at a speed of 19 miles per hour. Okay, now we have an exponential and we have a power rule mixed together in addition. So the derivative of this, let's look back at our rule. We have base e to the 0.5t. So the derivative of that will be ae to the ax. Now we do have this coefficient of 30 here, so that's still going to be there. But the derivative of just this variable piece right there will be 0.5 e to the 0.5t. And so we'll still have to multiply 30 times 0.5 in just a moment. The derivative of 7t is 7. And again, this is dt. Another function of time. So we get 30 times 0.5 is 15 e to the 0.5t. Plus 7. And if we want to evaluate this at time 2, we simply plug in t equals 2. And we get 15 e to the 0.5 times 2 plus 7. So we have 15 e to the 1 plus 7 comes out to about 47.8. And again, put that over 1 because that's the change in distance per change in time. So this is miles per hour. That's how fast we're traveling at that instant. A different value of time will produce a different instantaneous speed. Now in our final example, here we have a natural log and a base 4 log. So to take its derivative, again, we have a coefficient of 10, so we'll just focus on taking the derivative of that piece and then multiplying them back together. The derivative of log base e, which is ln. Okay, remember log base e is the same thing as ln. It's going to be 1 over x. So the derivative of the natural log of 0.2x, oh, I'm sorry, I should be using t's here, not x. This will be 10 times 1 over t. And now we have 3 times the derivative of this log base 4 of 0.5t, and that's going to be 1 over t times the natural log of that base. So times 1 over t times the natural log of our base, which is base 4. So if I compact this down, I get 10 over t plus, and I'll just leave this as 3 over the natural log of 4 times t. I could put in what the natural log of 4 is, but it's a little more exact to leave it like this. So I get that the derivative of distance versus time is 10 over t plus 3 over the natural log of 4 times t. So if I evaluate this at time 2 to determine my speed at time 2, I get 10 over 2 plus 3 times over the natural log of 4 times 2. And so the first term I know is going to be 5 plus 3 divided by, and I'm going to put in parentheses, ln 4 times 2, close parentheses, and I get approximately 6.1. Now once again, that's distance over time, change in distance over change in time, so this is going to be miles per 1 hour. So not only have we just reviewed derivative rules, but we've also applied it into context, so we see that this gives us useful information, and we're not just algebraically taking derivatives of functions, because our goal is to be able to apply this to solve real-world problems.